Get started.
This meeting is being recorded.
Okay, shall I start?
Yeah. So welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is Svetlana Puzynina, and she's going to speak to us about well-distributed occurrences in infinite words.
Thank you, Nared, for the introduction. So I will, during this talk, I will tell you about some abelian type property of infinite words. And I will start with the definition and some examples. Then I'm going to talk about some motivation. Actually, the motivation for studying this property comes from random number generation. Then I will discuss certain families of infinite words with this property. These families include Sturman words and Norasy words. And also I will discuss it for amorphic words. The talk is based on some old results and also some new results. So basically the story starts dating back some years ago when with Lubomira, Michelangelo, Alessandro and Giri, we started this research. And then there were some open questions left. And so with my student, Vladimir Shevelev, we attacked the problem about morphic words. Okay, so I will start with some notation. So throughout the talk, the alphabet will be the set of a set of integers starting from 0 and up to D. Sometimes the alphabet is binary, sometimes not. Then if we take W to be a finite word, we will denote its periodic vector by PV. So it's the vector counting the numbers of occurrences of each letter in the word. And these numbers are denoted as usual as follows. And for example, the periodic vector of this word is 3 to 2 because the word contains 3 occurrences of 0, 2 occurrences of 1, and 2 occurrences of 2. So then I will use the notation pref for prefix of a finite or an infinite word of a given length. So the pref n of u is its first n samples. Okay, so now I can give the main definition of my talk. So A is still the alphabet as on the previous slide, U an infinite word, and we ask it to be aperiodic. So we say that an infinite aperiodic word has the property of well-distributed occurrences, or I will denote it as well-doc, if the following condition holds. So I want that for each integer m and each factor of the word, when I consider the prefixes of this word preceding the occurrences of this factor w, then I want that their periodic vectors modulo m give all possible values. So let me show you that on the picture. So here is my word u, and I take all the occurrences of some factor w in the word u. I denote them by I1, I2, and so on. And so now I consider the prefixes preceding w. So this one, then the prefix of length I2, the prefix of length I3, and so on. And I consider their periodic vectors. So, and I want that these periodic vectors of these prefixes modulo m give the whole ZMD. And I want this condition to be satisfied for each m and for each factor w. So the property seems to be quite strong. No matter what integer I take, no matter which factor I take, I consider its positions and I get everything I can modulo m. Let's consider some examples. So, for example, consider the Fibonacci word, and I claim that Fibonacci word has this well-distributed occurrences property. I will prove it later for all Sturman words, and here I just give an example to illustrate the definition. So, for example, consider its factor 001, and the integer, I will choose it equal to 2. So here are the occurrences of this factor. I mark them by red. And actually, for me, now it's enough to consider its 4 first occurrences. Here I have the prefixes preceding these occurrences, the corresponding Parex vectors. And when I take these Parex vectors modulo m, which I took to be 2, I get everything. Well, I don't have to have it among the very first values, so I just need them to appear at some point. And we will prove that for the Fibonacci word, the property is satisfied for no matter which m and no matter which factor. So now let us consider the two-Morse word. So the two-Morse word, it does not satisfy this well-distributed occurrences property because, for example, we can consider the factor 0, right? So since the two-Morse word can be obtained as concatenation of the blocks 0, 1 and 1, 0 of length 2, then these occurrences of 0, the factor 0 occurs only at odd positions. So here I marked several first occurrences. So this means, for example, that for m equal to 2, since occurrences are odd, we have that the number of zeros and the number of ones when we sum them in the prefix is always odd. So which means that I cannot get all possible Parex vectors. The numbers of zeros and ones should be cannot be of the same parity for this factor. Let's consider some more examples. For example, if I take a universal word, universal means that it contains all finite words as its factors. Then it is easy to see that any universal word satisfies this well-distributed occurrences property. Well, indeed, we can see it right away. So take any m you want, take any word w you want, and we can easily arrange a finite word v, which contains this factor w at positions with prefixes congruent to vectors. Vectors from Z and D. We can arrange it simply by concatenation, by adding what we need and joining concatenated the correct prefix with the word W. And then now, since the word U, there should be U is universal. It means that it contains all possible factors, all possible words as factors, and including this word V, which already has all the prefixes we need. So, which means that our word, infinite universal word U, also has all vectors that we need. They're just shifted, right? Shifted according to the place where we put this V in the word U. So moreover, it has this occurrence is infinitely many times. Okay, so now say take recurrent words, any recurrent word you want, and then I just recall that word is recurrent if each its factors occurs in it infinitely many times. So let's remark that if a recurrent infinite word has this well-distributed occurrences property, then it means that for each vector from ZMD, there are infinitely many lengths of prefixes such that we have a prefix, periodic vector of the prefix congruent to V modulo M. So actually, when we consider words we normally like, which have this well-distributed occurrences property, then it's actually satisfied not just in one positions, but in infinitely many positions for each periodic vector from ZMD. So I mentioned that this property can be used in pseudorandom number generation. So what is pseudorandom number generator? Well, it is usually defined as some algorithm which produces a sequence which approximates a random sequence. So the aim of the pseudorandom number generators is to produce random numbers using a certain deterministic process. And the result, of course, is not at all random because we only start from something, some initial value, which is called the seed, which could be random in some sense. But then after that, all the process is determined. So this means that, of course, those pseudorandom number generators, they suffer from many defects, but they are still used because they are really fast to generate, and when we don't need a random sequence of very good quality, they are good enough. So for us, by pseudo-random number generator with an output a subset of integers, we would just mean an infinite word on this alphabet of integers. So basically, I consider this generator not as a process or an algorithm, and just as an infinite word on this alphabet of the output of the random number generator. So for me, this is just a word over this alphabet. To give an example of pseudorandom number generators, I suggest a linear congruential generator. This is a very simple, a very old way of generating pseudorandom sequences. So it is defined with three parameters, three integers a, m, and c, and we simply defined by recurrence relation. So each next value, we multiply the previous one by a, add a c, and take this modulo m. And so the sequence it produces, if we choose values a, m, and c good enough, then it is similar to a random sequence. But of course, this process is too simple to get a perfect random sequence. So these linear congruential generators, they have many defects. And one of these defects is called lattice structure. So lattice structure is the following thing. So let's consider our linear. Well, actually, it's not defined only for linear congruential generators. For any pseudorandom number generator, which I considered simply as an infinite word over alphabet m, which is finite. So we say that it has a lattice structure if there exists some integer, and then I consider the tuples of length t of its consecutive values. In other words, I consider the set of factors of the word z of length t. And if I consider it as a geometrical subset, because my alphabet is the alphabet of integers, then I can draw a picture, and if this is this set is covered by a family of parallel hyperplanes, and this family does not cover the whole lattice MT, then we say that the generator has lattice structure. And of course, if you have a random sequence, you can never have such a thing. You would cover everything. So here is I have here a picture of a famous old generator called Randu. It's a linear congruential generator with the parameters a equal to 2 to the power 16 plus 3, m is also a power of 2, and c equal to 0. So then we can take just t equal to 3. So we choose this integer 3. So which means that we can see the triplets, the factors of length 3 of this linear congruential generator. And then one can show that they are covered, the sets are covered by only 15 equidistant planes for m equal to 31 power of 2. So which is quite impressive how bad statistical properties it actually has. And so now I continue with words and how we can use them to for the generators. So the basic idea is the following. So I take two pseudo-random number generators, x and y, with the same output and the same period. And then I take a binary infinite word, any word I want, for example, Fibonacci word. And then I will build a new pseudo-random number generator based on this infinite word or according to this infinite word by mixing the previous two generators according to this to my word u. So I will replace all the occurrences of zeros in my word with the word x, and the occurrences of 1 I will replace with y. So for example, here I have the Fibonacci word. So I mark the ones by red to make it more visible. And then I take two words or generators, x and y, and I fill the zeros in u with x consecutively. And I fill the ones with y's consecutively. So this way, I obtain a new generator. So while I only gave definition for binary because it's easier to show in the picture, but of course you can do the same, absolutely the same thing by taking a non-binary word, word containing as many letters as you want, and mix several pseudo-random number generators, say linear congruential ones or some others, according to the word I choose. And the general idea is if you choose a word with good properties, and then so that it's fast to generate it, then the generator I gets better properties than the original ones. So several years ago with Michelangelo, Alessandro, Lubomira, and Giri, we proved that if you take an infinite word, u, satisfying the well-distributed occurrences property, and several linear congruential generators, then or pseudo-random number generators, then the resultant generator has no lattice structure. So basically, it means that mixing in this way gives you better generator than you had before. Well, here notice I would like to remark that this property of distributed occurrences is actually not necessary for absence of the lattice structure in the resultant generator, but it is sufficient. So as an example, we can take, for example, a modified Fibonacci word. So I take the Fibonacci on zeros and ones, and I insert the letter 2 after each occurrence of each letter. After each 0, if each 1, I put a 2. Then the resulting word, which I denote as u hat, clearly it does not have the well-distributed occurrences property. Like, for example, that because 2s occur only on even places. But however, it's not difficult to prove that if we mix 3 generators according to this word, then the result has no lattice structure. Now I continue with some families of infinite words and check if they have this nice, strong property, well-distributed occurrences. So I will recall that this property means that for each integer and each factor, when we consider the prefixes of this word preceding the occurrences of the factor, then we have all the vectors modulo the integer that we chose. Well, I will give one proof in this talk. So I will prove this property for Sturman words. This proof is the shortest, the simplest, and it looks nice because I will use the geometric definition and I can show it on the picture. So to prove this for Sturman words, I will use the definition of Sturman words with rotation. So I recall that the rotation by angle alpha is a mapping from the interval 0, 1, which is identified with unit circle, to itself. And we divide it as follows. We divide it as we take a point x in this interval, we add alpha to it. Alpha is, we'll take alpha to be rational. And then we take a fractional part so that we go again to the interval. So then, using this definition of rotation, I can define Sturman words. So I split the interval into 0, 1 into 2 intervals corresponding to 0 and 1, which I define as follows. And then I define the nth element, nth letter of the word as 0 if the corresponding rotation comes to the interval corresponding to 0, and to 1 if it comes to an interval corresponding to 1. Well, I'm slightly abusing the notation here because to get all the Sturman words like that, I also need to consider the intervals which are close to the right and not to the left. But if I take both, then I get all the Sturman words, and the proofs are pretty much symmetric for these two cases. So now I will prove the well-distributed occurrences property for Sturman words. So first, I will use the following trick. So instead of considering the pedic vectors of all prefixes modulo m, so the fact that I have all zm square modulo m among pedic vectors is the same thing as considering the length of the prefixes and the numbers of ones modulo m. Well, because if here I get everything, then the numbers with numbers of 0 I also get everything, because this I just need to subtract. So I can reformulate this statement, the well-distributed occurrences property, that among the prefixes preceding occurrences of each factor, if I consider vectors from lengths and numbers of ones, then modulo m, I get everything. And so now I need to control the length modulo m and the numbers of 1 modulo m. For that, I will take a circle of length m by copying m times the usual circle from definition, or the interval 0, 1 m times. And I will copy it with the corresponding intervals. So this one is I0, this one is I2, and then I take its copy and so on. So now recall that for a Sturman word, each is a factor w of my Sturman word u, which is defined as alpha rho, where alpha is this angle of the rotation and rho is some point. And then each factor corresponds to an interval. in 0, 1, so that if I start rotating from any point of this interval, then I obtain this word W. And since I took m copies of my interval, so here I can, for each factor W, I can take m corresponding factors. So in each copy I take W. So here, for example, I took it in the second copy and I marked the corresponding index by 2. Okay, so now to prove the well-distributed occurrences property for Sturman words, I need to do the following by definition. Well, not exactly by definition, by what I said, that I replace it with controlling numbers of ones and lengths. So I take arbitrary vector and any factor W I want, and I need to find the length of the prefix L such that the factor starting at position L of corresponding length is W, that the numbers of ones in the prefix modulo M is I, and the length of the prefix modulo M is J. So if I do it for each W, each J, and each I, then it means that I have what I need. So I will do it using this circle. I multiply them times and taking special rotation on it. So I will consider the rotation by angle M alpha instead of alpha on this M circle, and I will start at the position J alpha plus rho, where alpha and rho were the parameters of the original Sturman words. So what does this mean? So I take each time rotating by M alpha, it means that I just add, consider not the next position, but consider the position which is greater by M than the previous position. So which means that reading by this rotation what I see in the intervals, I will get a scattered subword of the Sturman words at the position congruent to J modulo M, like that. So, and J here, J I choose the one I need to get. So this J is exactly that J. And so now notice that the points in the orbit of this rotation on the M circle are dense. So this means that the rotations comes infinitely often to each interval. So I will choose the interval corresponding to W and the interval number I. So I for each factor W, I have M intervals, copies of the original interval on this big circle, and I choose the one corresponding to the interval I plus 1, the one which is from this interval. And then according to this observation that I come infinitely often to each one of these intervals, I will take the position, the place where I actually count the integer when I come to this interval. So I pick an integer k such that when I rotate k times by M alpha, I'm here. And so, which means that I actually have what I need for the length km plus j. So the fact that I rotated each time by M allows me to control the length. And the fact that I took a point from corresponding interval numbered I allows me to control the number of ones. So that's it. That's it. We proved the property for Sturman words. So now that's it. I'm done with the proofs. Now I will only give statements and maybe sometimes say general ideas. So actually, this statement about Sturman words, it can be generalized to Arno-Rosie words. Well, of course, because the Sturman words are a particular case of Arno-Rosie words, but actually for Arno-Rosie words, the well-distributed occurrences property is also satisfied. No matter which Arno-Rosie word you take, you will have it. So, of course, the proof for the Sturman words does not generalize to the Arno-Rosie words because they don't have such a nice geometric interpretation. So we have to come up with something different. And actually what we used the property, the definition via palindromic closures. And we proved the property for characteristic Arno-Rosie words. And then it follows that no matter which Arno-Rosie word you take, it has a well-distributed occurrence property. Well, of course, this property also works for Sturman words, but it's not as short as the previous one. So now the natural question is the following. So the original purpose of this well-distributed occurrences property was to build random number generators based on them. So which means that we need to be able to generate the word fast. So say for Sturman words, if a Sturman word is generated by a morphism, then we can generate it really super fast on fly, basically. And then it's very convenient to use it for the generation. So the natural question is, okay, why Sturman? Shall we probably consider morphic words and any kind of morphic words? So that they satisfy the well-distributed occurrence property. And so to give a characterization, not all morphic words, as we already saw, satisfy this property. Like, for example, tumors does not. We saw it taken particular factor. But we can give actually a characterization of morphisms satisfying this property. So to give the characterization, we actually only need the matrix of the morphism. So the matrix of the morphism is the matrix, square matrix, defined by the size of the alphabet, and on each place it has the numbers of occurrences of a letter I in the image of the letter J. And so with Vladimir Shavelev, we proved that if we have an aperiodic infinite binary word generated by a primitive morphism, then it satisfies the well-distributed occurrence property if and only if its matrix, the determinant of its matrix equals +1 or -1. So in particular, this gives the our statement for morphic Sturman words, because for morphic Sturman words, the determinant is 1. Now, I see the question in the chat. Okay, maybe I can answer that later. I need to digest this. Okay, so I will continue first with the words. So, like for example, if you take a two Morse word, then its matrix has a determinant equal to 0, so it doesn't have the well-distributed occurrences. While for the Fibonacci word, oops, I have a mistake there in the morphism. Of course, 1 goes to 0 for the Fibonacci morphism. So here is its matrix. And since its determinant is -1, so then it has a well-distributed occurrences. And of course, this all holds only for aperiodic words because the well-distributed occurrence property is defined only for aperiodic words. It's never satisfied for periodic ones, with a pre-period or without it. Now, this was for binary words. So what happens for non-binary words? Actually, we have a similar characterization, but here we would need an additional condition. So to state the characterization for non-binary morphisms, I will need a definition, a notion of a return word. So if you take U to be a recurrent infinite word, take V, sum its factor, and then I denote, as before, by ij the positions of occurrences of V in the word. And then, so the returns are the words which you read starting from the occurrence of W and ending just before the next occurrence of W. So basically, you split the infinite word into returns to V. So if you have a uniformly recurrent word, then you have finitely many. And of course, if the word is not recurrent, then you cannot define a return. And so we proved that for primitive non-binary morphisms, their fixed points satisfy the well-distributed occurrences property if and only if the determinant is +1 or -1, as before. And also we need an additional condition that pairing vectors of return words to the first letter of 0 generate the set that to the power of the cardinality of the alphabet. And this condition is automatically satisfied for binary alphabets, but for non-binary ones, we indeed need it. And here is an example. So consider the following morphism on 3 letters. It's primitive. And here is its matrix. Its determinant is 1. And so we need this additional condition. We need that the returns, to consider the returns to 0. And so here we have this returns. We have only 2. So when we take everything generated by these 2 vectors, we see that we do not have everything. For example, we always have the same numbers of zeros and ones. And so this means that this morphism does not have the well-distributed occurrences property. Also, I should say here in the statement, we only proved it for primitive morphisms. Well, actually, it might also hold either in this form or probably in slightly modified form for non-primitive ones. So the reasons why we put a primitive here is that we use one important property of primitive morphisms for the proof. This is the property of recognizability. So here is the precise definition of the property. So basically, the property of recognizability means that if you take a long enough factor of length to L, then it could be uniquely decomposed up to some short prefixes and suffixes. So the formal statement is there. There are many constant. I don't know how to put it in a short and brief way. And there are also several variations of these notions. This one is called often in the literature strongly two-sided recognizable. And due to a classical result of Mosse, which has been reproved several times, every primitive aperiodic morphism is recognizable. So we use this property and so basically, since this property is proved only for primitive words, then we had to put this condition. But actually, what we need in the proof is slightly weaker than the statement. So I guess there is probably another way to prove it without using this result, and to get the statement for all morphisms, not only for primitive ones. Yes, and also I should say that this additional condition on the prefixes and that it generates everything, that's actually quite easy to check algorithmically by the morphism. So there's it's quite an algorithmic criterion. So there are some conclusions I would like to say. So first, there's what I just said about the morphic words. Can we prove our characterization without using this complicated property? And this would probably give a simple proof, and which would also work for non-primitive morphisms. And another more like general direction is that we actually did some statistical tests with combining pseudo-random number generators according to infinite words with well-distributed occurrence property or not. And we showed that if you have well-distributed occurrences, then the resulting pseudo-random generator has better properties than the original ones. So of course, all the statistical tests, they failed at some point, but later than the original ones, while generating is as fast as the previous one. And so the general question is, okay, apart from this property of lattice structure, which we showed that we break with this well-distributed occurrences property, what other statistical properties of generators can be improved using words satisfying this well-dog property? Or can we probably use some other words properties to get generators with better statistical properties than the previous ones? So basically, that's what I wanted to talk about today. Thank you.
Thank you, Svetlana. Does anyone have any questions?
So may I have a question, Lubka?
Oh yeah, please go ahead, Lubka.
So thank you for your nice talk, Svetlana. And my question is just whether your paper is already available somewhere or in preparation.
Well, actually, it's very fresh. So we have some text, but we have not yet uploaded it to archive, but we're going to do it soon. Yeah.
Mm-hmm. Thank you.
So I didn't quite get the question from the chat. So basically, the idea is that the pseudo-random number generators, they produce numbers from certain finite set of integers, and such random sequences, they must satisfy certain properties. And of course, the like I don't know, fraction, the ratio of the numbers you have, the longest subsequence of the same integers, and so on. So you can check all those properties, and then the statistical properties, the tests, they do that. And of course, the pseudo-random generators, they fail test at some point. But when you take fairly short initial period, you cannot really distinguish it from the random sequence. So that's the point of using them. I'm not sure if I understood the question correctly from the chat.
I think the speaker has left also, so
okay.
Can't really clarify. I have one question. So for any class of words where you have this well-doc property like Sturmian words, Is there a bound? So given W and given M, is there a bound on the length of the prefix that you have to look at before you get all Parikh vectors modulo M?
Well, I guess you can have the bound, but I think that taking bad parameters for Sturmian words, it could take you quite a long time to get all the parameters. So I guess that depends on the actual word. And of course, when you also did the statistical test, it showed that some words give better result, others get worse. So it very much depends on the word. It's not only the mixing. It's not only these well-distributed occurrences.
All right, are there any other questions?
Maybe Svetlana, if I can have a comment. So in the history, as you mentioned, we studied the well-dog property, and then when I studied recently critical exponents of balance sequences, then this property was very important because when you construct balance sequences, then you color Sturmian sequences by so-called constant gap sequences. And in order to understand well the balance sequences, it was important to have this well-dog property for Sturmian sequences. So it was my second time that I met the well-dog property, and where it played a very important role. So just this comment.
Yeah, well, actually, this is the point that the way we obtain any balanced sequence from a Sturmian word, this is exactly how we mix the random generators according to a word. So this is a very essentially this is the same construction.
Yes.
Any other questions? If not, thank you very